Hello, everyone. Today we're going to go over the homework for sections 2.1 and 2.2. Let's start with the section 2.1 homework and take a look at number 1. For each situation, we want to describe the sample space and the event space. In number 1, we want to roll a 20 on a 20-sided die. So the options for what we can roll, the sample space, would be a 1, a 2, a 3, a 4, all the way up to 18, 19, or 20. And the event that we're interested in is rolling a 20, so there's only one in the event space, and that's 20 itself. Now, we're not finding the probability of rolling a 20, we just want to describe the sample space and the event space. But if we were looking for the probability, that would be 1 out of 20. In number 2, we want to draw an ace from a standard deck of playing cards. The sample space is a little bit too big to list out, but it would contain the 52 playing cards, the ace of spades, the 2 of spades, all the way up through the king of spades, and then all the clubs and all the diamonds and all the hearts. There would be 52 in the sample space. We're interested in the event of drawing an ace. There are 4 aces in the deck, the ace of hearts, the ace of diamonds, the ace of clubs, and the ace of spades. So there are 4 in the event space. Number 3. So I mentioned before in the directions for the homework that this is easier after we discussed the methods of counting in section 2.2. So this was a lot easier after section 2.2. But we're interested in getting a total of 5 when rolling 3 6-sided dice. We have the counting principle, where when we're doing independent events, we can multiply them together. The first of the 6-sided dice would have 6 outcomes. The second of the 6-sided dice would have 6 outcomes. And the third of the 6-sided dice would have 6 outcomes. So we can multiply those together, 6 times 6 times 6, and there would be a total of 216 possible outcomes in the sample space. They would be 111, 112, 113, 114, etc., etc. All of the different combinations that we can get rolling 3 6-sided dice. Now, in terms of totals of 5, that would be our event space, what we're actually interested in. We must list the possibilities in an orderly manner. We can list out all the ways to get a total of 5. Either we roll a 1 first, a 1 second, and a 3 third, or a 1 first, a 2 second, and a 2 third, or a 1 first, a 3 second, and a 1 third. Those are all of the different possibilities where we roll a 1 first. Looking at the possibilities where we roll a 2 first, we can roll a 2, then a 1, then a 2 to give us 5. Or we can roll a 2, then a 2, then a 1 to give us 5. And those are all of the possibilities of rolling a 2 first and getting a 5. And then we only have one possibility of rolling a 3 first and getting a 5, and that would be 3, 1, 1. There wouldn't be any possibilities starting with 4 because we could roll a 1 second, and that's already 5. There's no room to roll anything the third time. So there's just 6 possibilities in our event space: 113, 122, 131, 212, 221, and 311. In number 4, this is another one that's easier. After section 2.2, using the counting principle, we want to flip 6 coins in a row, never getting heads or tails twice in a row. So if we flip 6 coins in a row, there are 2 outcomes for each of the 6 coin flips, either heads or tails. So 2 for the first coin flip, 2 for the second coin flip, 2 for the third coin flip, 2 for the fourth coin flip, 2 for the fifth coin flip, and 2 for the sixth coin flip. That's 2 multiplied together a total of 6 times, or 2 to the 6th. There would be 64 possibilities of what could happen when we flip 6 coins in a row. So the sample space would have 64 items, all heads but one tails at the end, so on and so forth. All of the different possible combinations of heads and tails. There'd be 64 of them. The important thing is knowing that there's 64, not actually listing all 64 out. Now, in terms of never getting heads or tails twice in a row, which would be the event space, we must again list the possibilities in an orderly manner. If we start with heads, since we want never getting the same thing back to back, the next one would have to be tails, then heads, then tails, then heads, then tails. If we start with tails, then we would have to alternate heads, tails, heads, tails, heads. And those are the only two possibilities for flipping 6 coins and never getting heads or tails twice in a row. So there's 2 possibilities in the event space. Heads, tails, heads, tails, heads, tails, tails, heads, tails, heads, tails, heads. Number 5. Again, we're describing the sample space and the event space. We want to pick a red ball from a pot containing 4 red balls, 5 blue balls, and 3 green balls. We're picking 1 ball out. So in terms of all possibilities, our sample space, there are 3 outcomes. We could either pull red, blue, or green. The sample space would be red, blue, green. In terms of picking a red ball, that is the only outcome in the event space. So the event space would be red. The fact that there's 4, 5, and 3 does not come into play here because we're only describing the sample space and the event space. We're not finding probabilities. Number 6, we're going to switch up what we're doing. We want to find the probability of an event which has the given odds. In number 6, we're given that the odds for the event are 5 to 2. Since the formula for odds for is NE over NE star, that means NE must be 5 and NE star must be 2. The number in the event space is 5. The number in the complement of the event space would be 2. We can use NE and NE star to find NS. Our formula says we just add NE and NE star together to get NS. So NS must be 5 plus 2 or 7. Finally, probability is NE over NS. The probability then would be 5 over 7. NE was 5, NS was 7. So 5/7 is the probability in number 6. In number 7, we're given that the odds for are 7 to 12. Again, the odds for would be NE over NE star. So NE must be 7, NE star must be 12. We add those together to get NS. So 7 plus 12 is 19. N of S is 19. And finally, the probability of the event would be NE over NS. NE is 7. NS is 19. So the probability of the event is 7 over 19, 7/19. Number 8, the odds for are 11 to 1. Again, odds for is NE over NE star. That means NE must be 11, NE star must be 1. Add those together to get NS. NS is 11 plus 1, NS is 12. And the probability would be NE over NS. That would be 11 over 12, 11/12. Number 9, now we're given the odds against are 3-2. Odds against is the reciprocal of odds for. Odds against is NE star over NE. So that means NE star is 3. NE is 2. Add those together to get NS. 2 plus 3 is 5. So NS is 5. The probability of the event is NE over NS. That would be 2 over 5, 2/5. In number 10, again, we're given odds against, NE star over NE. The odds against are 11-1, so NE star must be 11, NE must be 1. If we add these together, 1 plus 11 gives us 12, so NS is 12. Finally, the probability is NE over NS. That would be 1 over 12, 1/12. The directions change up here with number 11. We want to find the odds for and the odds against an event which has the given probability. So instead of giving us probability, it's giving us odds for. So we already have that. The odds for are 5-8. The odds against would be 8-5. Remember, odds for and odds against are reciprocals of each other. We just switch the numbers around. So if the odds for are 5-8, then the odds against are 8-5. Same thing in number 12. We're given the odds against as 7-1. So we have the odds against 7-1. The odds for would be 1-7. We just switch the numbers around between odds for and odds against. Number 13, they give us a probability. The probability they give us is 5/8. And since probability is NE over NS, that gives us NE and NS. NE would be 5, NS would be 8. Now, using our NS equals NE plus NE star formula, we would have 8 equals 5 plus NE star, which implies that NE star is 3. So now we have NE and NE star. We can find the odds for, which would be NE over NE star, 5/3, so 5-3. And the odds against are the flip of that, 3-5. Number 14. This time we're given a probability of 3/7. So that tells us that NE is 3 and NS is 7. Using our NS equals NE plus NE star formula, plugging things in, we get 7 equals 3 plus NE star. That implies that NE star must be 4. Now we have NE is 3, NE star is 4. NE over NE star gives us 3/4. The odds for are 3-4. And when we flip that around, we get the odds against. That would be 4-3. Number 15, we're given a probability of 11/63, 11/63, which means NE is 11. NS is 63. Plugging those into the NS equals NE plus NE star formula. 63 would equal 11 plus NE star. NE star is implied to be 52 then. NE over NE star gives us 11/52, so the odds for are 11-52. Flip that around for odds against, and we get 52-11 for the odds against. Number 16. A standard deck of playing cards is shuffled, and the top 2 cards are revealed to be the 8 of spades and the 5 of diamonds. These cards are set aside, and then another card is drawn from the remainder of the deck. What is the probability that the new card is a diamond? Is question A. So we have 50 remaining cards. The sample space would be the 50 remaining cards, and the number in the sample space would be 50. We pulled a diamond out earlier, so instead of 13 diamonds, there are 12 remaining diamonds. So the probability of pulling a diamond as our new card would be 12 out of 50, which reduces to 6 out of 25. Question B, what is the probability that the new card is an 8? Well, there's usually 4 8s in a deck, but we pulled out the 8 of spades earlier, which means there are 3 remaining 8s. So 3 out of the 50 remaining cards would be the probability that the new card is an 8, 3 out of 50. And finally, what is the probability that the new card is the 8 of spades? Well, we pulled that out of the deck earlier. So there is no probability that the new card is the 8 of spades. It's not one of the remaining cards, so 0 out of 50, or 0 for the probability. Number 17. In one particular board game, movement is determined by rolling a 12-sided die. A, what are the odds in favor of rolling a 10 or higher? So the sample space is 1 through 12. That means N of S is 12. There's 12 possibilities in the sample space. We can roll a 1, we can roll a 2, we can roll all the way up to a 12 on a 12-sided die. The event space of rolling a 10 or higher would just be 10, 11, and 12. That means N of E, the number of things in the event space, is 3. If N of E is 3, N of E star, the complement, would be the other 9 that are not in the event space. So the odds for are NE over NE star, 3 over 9, 1 over 3. When we write that as odds, that's 1 to 3. Question B, what are the odds against rolling a 4 or lower? So the sample space is still 12, but rolling a 4 or lower would be 1, 2, 3, 4 in the event space. N of E then would be 4. N of E star, the complement of that, would be the 8 not in the event space. Odds against are N of E star over N of E, that's 8 over 4, which is 2 over 1. And as odds, the odds against would be 2 to 1. Number 18. In a simple casino game, each player is dealt 3 cards from a 5-suit deck of cards. You win $15 if at least 2 of your cards are the same suit, which will happen in 30% of hands dealt. Otherwise, you lose. If it costs $5 to play, what is the expected value of a hand in this game? So the text had a different number that you win, but in order for the answer to work out, you actually have to win $15. If you win $15, you're actually only winning 10 because 5 of that was already yours. So you have to subtract your $5 from the $15 you win, meaning that the one outcome is that you get $10. The probability from the problem is that that'll happen in 30% of hands dealt. Probability of 30% is 0.3. We multiply the $10 times the 0.3. We get an outcome times probability of 3.00. The other outcome, which happens 70% of the time, is that you lose $5. So minus $5 times the probability of 70%, so times 0.7, would be negative 3.50. If we add this column together, we get an expected value of negative 0.50 or negative 50 cents. So the expected value of a hand in this game is negative 50 cents. On average, over the long run, you will lose 50 cents per hand playing this game. Number 19. In a carnival game, it costs $1 for one roll of an oversized 12-sided die. If the one red face on the die comes up, you win $5. If any of the three blue faces on the die come up, you win back your $1. Otherwise, you lose. What is the expected value of one try at this carnival game? So let's look at the possible outcomes. If the one red face on the 12-sided die comes up, you win $5. It costs $1, so you're actually only getting $4, $5 minus your $1. That was one red face out of 12 sides, so the probability would be 1/12. If we multiply the $4 times the 1/12, we get 0.33 for that row. Then we have the outcome where you win back your dollar. In other words, the outcome is $0, $1 minus your dollar that you started with. This happens 3 out of 12 times because there are 3 blue faces on the 12-sided die. 3/12 reduces to 1/4. If we multiply 0 times 1/4, we get 0 for that row. Then there's the outcome where you just straight up lose your dollar. There were 4 faces accounted for with the red and the blue sides. That leaves 8 out of 12 where you lose. 8 out of 12 is 2/3. The negative $1 times the 2/3 gives us negative 0.67. If we add up the outcome times probability column, we get negative 0.33. Maybe negative 0.34, depending on how you rounded these. But the expected value of one try at this carnival game would be that you lose 33 cents or 34 cents, depending on how you rounded. Number 20. At a horse racing track, a bookmaker has set the odds against Quality Storm winning at 11-1 in the morning line. Assuming poorly that betting odds are given as the horse's chance of winning, what is the probability that Quality Storm wins today's race? So we want the probability of winning. We have the odds against as 11-1. So what do we know from that? Odds against is NE star over NE. That's 11/1. So NE star is 11 and NE is 1. We add those together to get NS. NS would be 1 plus 11 or 12. So the probability would be NE over NS. That's 1/12. 1/12 is the probability that Quality Storm wins today's race. Continuing from number 20 and number 21, what is the expectation value of a $1 bet on Quality Storm? Why does this show that our assumption that betting odds are given as a horse's chance of winning are a poor one? The odds 11-1 tell us that you make $11 for a $1 bet. 11-1. If we do the expected value table, the outcome of $11 has a probability of 1 in 12. How do we get probability of 1 in 12? Well, we add NE and NE star 11 and 1 to get NS. And then NE would be 1 because this was odds against. NS was 12, probability of 1/12. $11 times 1/12 is 0.92. The outcome of losing our dollar then would happen 11 out of 12 times, since it has to add up to 12 out of 12. -1 times 11/12 is -0.92. So the expected value is 0. We would call this a fair game. However, the people running the betting have to make money somehow, so something isn't right with our assumptions. So that's why it shows that our assumption that betting odds are given as a horse's chances of winning are a poor one, because there's no room for the house to make money. And the house always wins. Number 22. A 45-year-old woman in the United States has a 0.2192% risk of dying during the next year. An insurance company charges $410 for 1 year of coverage with a life insurance policy that pays a $150,000 benefit in the event of death. What is the expected value for the person buying the insurance? So some math, first of all. You're not actually getting $150,000. You've paid $410. So if we subtract that, you actually get $149,590. That happens 0.2192% of the time. That's 0.002192. If we multiply that times the 149,590, we get 327.90128. Then there's the outcome where you lose your $410. And since this is life insurance, that's actually the good outcome because you're still alive. But the outcome of losing $410 would happen 100% minus 0.2192%, or 99.7808% of the time. As a decimal, that's 0.997808. And if we multiply that by the -410, we get -409.10128. Add up the column, the 327 point whatever, plus the -409 point whatever, and we get -81.2. So the expected value for the person buying the insurance is that they lose $81.20. So that is the section 2.1 homework. Let's move into the section 2.2 homework. For each situation, we want to determine the total number of possible outcomes. We're going to use that strategy where we have independent events and we multiply all of the possibilities together to get the final number of outcomes. In number 1, we're rolling 2 8-sided die. There's 8 possibilities for the first die, 8 possibilities for the second die. That's 8 times 8, or 8 squared, which is 64 outcomes. Flipping 10 coins. That's 10 times where we have 2 possibilities. So 2 times 2 times 2, a total of 10 times. That's 2 to the 10th, or 1,024 outcomes. Number 3, each item in a database is identified by a 3-letter identification code. Well, the identification code is 3 letters, and there's 26 letters as a possibility for each of the 3 letters in the code. So 26 times 26 times 26. That would be 26 cubed, or 17,576 outcomes. In number 4, we're rolling a 20-sided die and a 4-sided die. That's 20 possibilities for the first, 4 possibilities for the second, a total of 20 times 4, or 80 outcomes. Number 5, we want to draw a card from a standard deck of playing cards, set it aside, then draw a second card from the same deck. So for our first draw, there are 52 possibilities, but then we take that card and set it aside. So for the second draw, there are 51 possibilities. 52 times 51 gives us 2,652 outcomes. Now, with number 6, we're no longer multiplying independent events together. Instead, we're reordering. So we have the 6 teams in the local sports ball league are ranked from best to worst. Sports ball. So we're reordering 6. How many different ways can we do that? Well, that's the factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. There are 720 ways to reorder the 6 teams. Same thing with number 7. 7 guests must be seated across the front of a stage for a panel. So we're reordering 7. How many different ways can we do that? That's 7 factorial. So 7 times 6 times 5 times 4 times 3 times 2 times 1. 5,040 ways to reorder those 7 guests. Number 8. The face cards in a standard deck, the Jack, Queen, and King of each suit, are shuffled together. So that's the Jack, Queen, and King of Ace, of Hearts, of Spades, and of Clubs. So there's 4 suits. We're looking at 3 cards from each suit. That's 12 face cards in a deck. We want to reorder those 12. How many different ways can they come up? That's 12 factorial. So 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that works out to 479,001,600. So if you shuffled together the face cards from a standard deck of cards, you'd have 12 cards, and there would be 479,001,600 different ways for them to come up. In number 9, Laura has 5 different kinds of coffee and wants to drink a different one before work every day this week. So we want to reorder the 5. That's 5 factorial. 5 times 4 times 3 times 2 times 1. There's 120 different ways that Laura can drink the 5 kinds of coffee, having a different one each day. Number 10. Pressing shuffle randomizes the order that the 11 songs on an album will be played. So we want to reorder 11. How many different ways can these 11 songs come up? That's 11 factorial. 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 39,916,800 different ways these 11 songs can be played. In one particular card game, play starts by taking all of the diamond cards from a standard deck of cards, shuffling them together, and turning the top card face up. How many different possible ways are there to start this game? It doesn't say how many different ways can they come up, all 13 of them, just for the first move, just to start. And the sample space contains our 13 diamond cards. There are 13 possibilities. Therefore, there are 13 ways to start this game. Be careful. This was not 13 factorial because we were just interested in starting the game. We were just interested in the first turn. Number 12. A fair coin is tossed 4 times. What is the probability that all 4 coin tosses land on the same face, either all heads or all tails? So first we would need the sample space, and we're tossing a coin 4 times. Each of those 4 experiments, we'll say, has 2 possible outcomes, heads or tails. So 2 for the first coin times 2 for the second coin times 2 for the third coin times 2 for the fourth coin would be 2 to the fourth, or 16 different possibilities that can happen. N of S then would be 16. The event space would only have 2 possibilities, either all heads or all tails. Heads, 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 tails, 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 tails. The event space has 2 possibilities. N of E is 2. Probability of the event is N of E over N of S. That's 2 over 16, which reduces to 1/8. Number 13. In one board game, actions are resolved by rolling an 8-sided die and a 12-sided die. If the 2 dice match, the action fails. Otherwise, it is successful. What is the probability of failing an action in this game? So we're rolling an 8-sided die, that's 8 possibilities. We're rolling a 12-sided die, that's 12 possibilities. We're multiplying those 2 together, 8 times 12. There's a total of 96 possibilities. The sample space contains 96. N of S is 96. The event space contains all possibilities of the 2 dice matching. So there would be 8 in the event space. Why not 12? Well, we're looking at the event that the 2 dice match. One of the dice only has 8 sides. So not having numbers 9 through 12, there cannot be a match there. So we could only match 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6, 7 and 7, or 8 and 8. So the event space contains 8. N of E is 8. The probability is N of E over N of S. That's 8 over 96, which reduces to 1/12. 1/12 is the probability of failing an action in this game. Number 14, in a different board game, movement is determined by rolling 3 6-sided dice and adding the results together. How many different possible outcomes are there for rolling these dice? And what is the lowest and the highest possible result after adding the dice together? So we're rolling 3 6-sided dice. That's 6 possibilities for the first die, 6 possibilities for the second die, and 6 possibilities for the third die. 6 times 6 times 6, or 6 to the third, gives us 216 possible outcomes just for rolling the dice. As for the lowest and the highest possible result, the lowest sum would have to be getting the lowest number on each. So 1 plus 1 plus 1 would be a lowest sum of 3. The highest sum would have to be getting the highest result on each. So 6 plus 6 plus 6 would give us the highest sum of 18. Number 15. In the game we saw in number 14, movement is determined by rolling 3 6-sided dice and adding their results. Joy will win the game if she gets a 5 on her next roll. What is the probability that Joy wins on the next roll? So again, the sample space hasn't changed. That's still 6 to the third or 216 possible outcomes just for rolling the dice. The event space we're interested in will be rolls where the 3 dice add to give a sum of 5. How can we get a sum of 5 on 3 die? Well, that's 1 plus 1 plus 3, or 1 plus 2 plus 2, or 1 plus 3 plus 1. Those are the ones where we roll a 1 first. Those are all the possibilities of getting 5. Rolling a 2 first, we would have 2 plus 1 plus 2, and 2 plus 2 plus 1. Those are all the possibilities of getting a sum of 5 by rolling a 2 first. And the only possibility of getting a sum for 5 rolling a 3 first would be 3 plus 1 plus 1. Again, just like previous problems, in this case, rolling a 4 first would not leave any options for giving a sum of 5 because 4 plus 1 plus some other number is already over 5. So there are 6 events that give us a sum of 5. N of E is 6. So the probability is N of E over N of S. That's 6 over 216, which reduces to 1/36. So this should say exercises 16 and 17 at the top. Apologies for that, but these are the last 2. A Chinese restaurant's menu invites the customer to choose 1 of 5 meats, 1 of 7 sauces, and 1 of 4 sides to create their meal. If they wanted to change their menu to instead list out every meal they can make with those combinations, how many items would they have on the menu? So the sample space would contain 5 meats times 7 sauces times 4 sides, which would be a total of 140 items. 140 meals can be made out of those combinations. Finally, number 17, a squirrel visits each of its 7 larders every day. It changes the order in which it visits every time in order to confuse predators. How many times can this squirrel visit its larders without repeating the order? We want to know, how can we reorder 7 things? That's 7 factorial. So 7 times 6 times 5 times 4 times 3 times 2 times 1 would be 5,040 different ways that the larders can be visited in different orders without repeating. Okay, next time I see you, we're going to go ahead and do section 2.3 material.